Thank you for joining me for this discussion of an old exam question about galvanic cells. Thank you to Tsepo for asking for this question. This comes from the Eastern Cape Trials examination from 2019. And here you can see the question displayed. It's question 8. What you should do now is pause the movie. If possible, download the question from the link that I give below, and then work through it yourself before continuing with this movie. So we can see that this is a galvanic cell. How do we see that? It's not an electrolytic cell because there is no battery. This is the battery. So that tells us that we're going to have a spontaneous chemical reaction occurring to create a potential difference between the two electrodes that we see. Let's first make sense of the galvanic cell that we're given, and then we'll worry about the questions. Let's start by looking at the components of the cell. We can see that there are two half cells which are joined by an ion bridge as well as an external circuit. And the first question actually asks about that ion bridge. What is the purpose of it? So one of the things is that, like the external circuit, it completes the circuit so that we have a continual path of conductors. It's not a conductor in the same sense as the external circuit's wires are, but it is a conductor in that it allows charged particles to move. It allows ions to move, and that is its purpose. It allows ions to move between the two half cells. And why is that important? Because otherwise we don't have a complete circuit, and also that helps to equalize the buildup of charge inside the two half cells, or reduce the buildup of charge, because it allows charges to move through the ion bridge to reduce that. Then let's look at the components of each of these half cells. We can see that we have platinum as one of the electrodes. Don't let that confuse you. Platinum is used here because it's inert. It's acting as an inert conductor of electricity, but it itself is not participating in the reaction. So let's ignore its presence. And then let's write a list of the other chemicals that are involved here. We can see that we have an iron electrode, and it is in a solution of its iron 3+ ions. And then in the other half cell, we have bromine, and it's together with a solution of bromide ions. So we can see that we have elements and their ions. And what's going to happen is that these are going to react between one another. One is going to turn into the other, and we need to figure out which way is the reaction going to happen. To help us to do that, we need to look at a table of standard reduction potentials. Now, if you look in the examiner's reports for the last few years, you will see that they keep saying students don't know how to use this table. So let's spend a bit of time understanding what this table says and then applying it to this particular question. In the South African examination data sheets, we are given two such tables, and I'm going to be referring to table 4B. How do we recognize that one? We see that lithium is in the top right and fluorine is in the bottom left. This is important. Why? Because in this particular version of the table, on the right, we get reducing agents, and the higher up on the right, the stronger the reducing agent. Lithium is a very strong reducing agent. Lithium is an alkali metal. All the alkali metals are very generous. And the scientific way of saying that is that they're strong reducing agents. Why are they so generous? Because the alkali metals have only one valence electron in each atom. And if they could just lose that one valence electron, that would reveal the stable noble gas electron configuration underneath. And so that's why they are very easily oxidized, meaning they lose electrons. Something that's oxidized is a reducing agent. Then let's go to fluorine. Fluorine's at the bottom left. Fluorine is a halogen, and it's the most reactive of all the halogens. Halogens have 7 valence electrons, just one gap in each atom. And if they could just get someone to give them an electron, they could fill that gap. And then they would have a stable electron configuration of a noble gas. That is why they are so greedy. Put in correct scientific language, they are very strong oxidizing agents. So in this table, the lower down on the left something is, the stronger it is as an oxidizing agent. And oxidizing agents are reduced. How are they reduced? By taking in electrons from the reducing agent, which is oxidized. Now, how do we decide in this particular example which of these items is going to be the reducing agent and which is going to be the oxidizing agent? Well, because it is a galvanic cell, the strongest oxidizing agent is going to be the oxidizing agent, and the strongest reducing agent is going to be the reducing agent. They get to be what they're strongest at in a galvanic cell. So all we need to do is check the position of these items within our table. And when we do so, we find that amongst them, iron is the highest on the right, changing into Fe3+. And we find bromine lowest down on the left, changing into bromide. So for a galvanic cell, when we're using table 4b, we read the reaction that happens in a C formation. So that tells us that in this particular question, our oxidation half reaction is going to be iron being oxidized to iron 3+, and that happens with the loss of 3 electrons per ion. And we can see that our reduction half reaction is bromine being reduced by the gain of electrons to the bromide ion. Now, before we get to the questions, let's look at this just a little bit more. We know that oxidation always happens at the anode, and that's easy to remember because they both start with a vowel. And we know that reduction always happens at the cathode. So this is true whether we have a galvanic cell like here or even in an electrolytic cell. That oxidation always happens at the anode, reduction always at the cathode. Right, now let's take a look at our questions. The first question we've already answered. The second question asks us which of these half cells is the cathode. And we've seen that it's the bromine half cell, which is half cell A. Next question, it asks us to give a balanced equation for the redox reaction. So we haven't quite got that yet. Notice that our electrons are not balanced. There are more electrons given than taken in. And that's just not possible because what would happen to those electrons? We have to account for them. And so we need to multiply both of these reactions by something so that we balance the electrons. Can you see that we must multiply this top one by 2 and this one by 3, and then we have 6 electrons given for every 6 taken. Now we simply write the whole redox reaction. Don't forget to do your multiplication, 2Fe, and we can give the phase, that's solid, plus 3 bromine, Br2, and that's liquid. We don't need to write the electrons because we already know we've got 6 on either side, so that cancels. 2Fe3+. With these equations, you can't be lazy and just leave off something like a 3+, because Fe3+ and Fe means something very different. And similarly, with the bromine and the bromide, don't leave off that minus. Notice the 6, 2 times 3. So here we have our balanced equation. And you can indeed see we have 2Fe, 2Fe, of course that's 3+, and 6 Brs, 6 Brs. Remembering, of course, that this is minus actually. Next question, 8.4. We're asked to find what the starting potential is of the cell. And we notice in the question that this is under standard conditions. So this question is asking what is the standard potential difference of this cell? And we know that the formula is standard potential of the cathode minus the standard potential of the anode. And be careful not to simplify this to make it wrong by just saying something like cathode minus anode. So what do? We simply go to our standard reduction potential table and we find the standard potential of the bromine cathode. And from that we subtract what we find for the iron. Make sure that it's the Fe and Fe3 plus line within the table. From the table we find that this value is 1,07 volts and this one is minus 0,06 volts. Watch what I did with the signs. Be careful there. We know that minus times minus is plus. So we have 1,07 plus 0,06 volts, and that gives us 1,13 volts. Last question. We're asked that if instead of using bromine at the cathode, we rather have iodine, what would happen to this potential difference across the two electrodes? Now we know that iodine is also, like bromine, a halogen. So we have a very similar kind of reaction occurring. But how do they compare? Like I said before, fluorine and bromine and iodine, since they are halogens, they are very strong oxidizing agents. They're very greedy. They like to be reduced very readily. But there is a trend amongst them. And we know that the higher up on the periodic table, the smaller the halogen is, obviously, because that means it has fewer electrons, therefore it has fewer electron shells. And the smaller it is, the more greedy it is. Fluorine is the smallest halogen. It's the highest up on the periodic table of the halogens. And so it's the most greedy. It's the strongest oxidizing agent amongst the elements that they are. Why? Because being so small, the valence shell is very close to the attractive force of the nucleus. And so that's why it can attract another electron, being a very strong oxidizing agent as a result. And then the trend is that as you go downward on the periodic table, of course they become bigger and bigger. That valence shell is then further and further from the attractive force of the nucleus. And so therefore they become weaker oxidizing agents. They're still very strong oxidizing agents, but weaker. So from their positions on the periodic table, we can see that iodine, being lower down, is a weaker oxidizing agent than bromine. Or if we come here to our standard reduction potential table, we see that bromine is lower down on the left than iodine is. And that tells us bromine is a stronger oxidizing agent than iodine. In other words, bromine is more greedy than iodine. So if we take this greedy one away and we put a less greedy one there, then can you see that the potential difference we get is not going to be as great? But we can also go and do it by numbers. And we take a look at the electrode potential of the cathode if it is rather iodine, not bromine. And we find it to be only 0,54 volts. And so if we add that, we find the answer to be only 0,6 volts. So that kind of cell would have a lower potential difference than the bromine one. So, if you enjoyed that, don't forget to like and subscribe and leave comments below. What did you learn? What do you still need help with? And what other topics should I make movies about? Thank you, Tsepo, for suggesting that I make this movie. Everyone else, your request will also be honored.